Hello class. We begin the course of stochastic process. Uh, the PDF of the all course upload in LMS site. You can download and print and study step by step. But we assume that you study and pass a course or two course in BS for BS degree in university, so you must learn and know some detail, same as experiment, random experiment, event, probability density, probability, mass function, cumulative distribution, and expected value, variance, random variable, and so on. So you can read from chapter 1 up to end of chapter 9 the subject that we need to study the course of random process. So begin the lesson. Basic concept of a random process. In real life application, we often interested in multiple observation of random values over a period of time. For example, suppose that you are observing the stock price of a company over the next few months. In particular, let ST be the stock price at time t. T is a number in this interval. Here we assume t equal to 0 refer to current time at begin. Okay, at begin. Figure 10.1 shows a possible outcome of this random experiment from time t up to time 1, means in 1 month. Okay, uh, the high represent the stock price, and this axis show the time. Okay, in each time how much the stock price. Okay, so a possible realization. Okay, this figure means realization. uh, when we see the data, that at each time how many st can take, this is realization value of a stock observed as function of time. Okay, means s of t is a function with argument is t. Okay, this is example of random process. Not that any fixed time t1 in this interval st1 is a random variable. Means for each fixed t, xt is a random variable. Come back and study means of random variable. Based on your knowledge of finance and historical data, you might to able to provide a PDF, okay, PDF probability density function. Go back in previous chapter of book that upload above, same as this, okay, same as this. This is probability density function that denoted by PDF. Okay, uh, so uh, at each time, st is a random variable. For example, at time t2, t index 2, st index 2 is another random variable. st1 have has probability density function, st2 has probability density function. These two probability density function may be different from each other, okay? So st for each t in this interval collectively, okay, collection, okay, for each t you have the value of st1. So you have collection of value, collection of random variable. This is called random process or stochastic process. Okay, so a stochastic process in general definition is collection of a random variable that take the value at each time. This process denoted by this notation. Therefore, a random process is a collection of random variable, usually indexed by time or sometimes by space. Okay, t maybe time, maybe space. Okay, so definition of a stochastic process, a random process is a collection of random variable usually indexed by t. The process st mentioned have here is an example of continuous time because the price of a stock at each time take to be a value, okay, is continuous random variable, random process, okay. Time, continuous time random variable. If time is continuous, the process is called continuous time random variable. If t is discrete, then the process is called discrete time random process. Okay. When we have a random process xt where t can take real value in an interval on the real line, then xt is a continuous time random process. For example, let nt be the number of customers who have visited a bank from t equal to 9. A bank open at time 9, okay? After this time, at each time that is continuous, time is continuous, we can know that how many people enter to bank. For example, at this interval, okay, at this interval between 9 up to 16 o'clock, at each time we can say that how many people in uh, in come into the bank. Okay, for example, uh, the bank opened at time 9. Okay, so at first n9 equal to 0. But when time span and t take the value in this interval, because a number of people that entire to the bank maybe 0, 1, 2, take one of this value for this time. So you can say that at T1, how many people come to bank? Okay, T1 is a time that greater than 9. Okay, another example, let omega W be thermal noise voltage generated across a resistor in an electronic circuit. Okay, each transistor uh, produce heat. Okay, heat uh, produce noise in the system. Okay, so at time t, measure noise or measure heat. Okay, here Wt can take real value. For example, thermal. Okay, let T, T of T, temperature at a city same as New York at time t equal to belong to 0 up to infinity. We can assume that t is a measure in ohm at t equal to 0, refer to time when we start measure temperature. In all of these examples, we are dealing with an uncountable number of random variables, okay? Because t take any time. So t of t is in uncountable sequence, okay? But in some in this is for continuous time, okay? If so, time can be continuous, time can be discrete, that time is index. The value of s or x um, that take may be continuous or discrete. So in the above example, t is continuous and the value of omega take is continuous. But for this example, n of t, t is continuous, but the value that n may take is discrete. You take a break and come back. On the other hand, you can have a discrete time random process. A discrete time random process is a process same as this notation, okay, where G is a countable set. G we can compute the number in G, okay, 1 2 3, okay, we can numerate where G is a countable set. Since G is a countable, we can write same as this, okay, G first value, second value, and so on. We usually define when the random variable is discrete time random variable, we can define by this notation x parenthesis t of n. We can write xt, or we can write x index n for n equal to 1, 2, and so on. N is called index value, okay, but uh, x is a state value, okay. uh, T can uh, G G may be a subset of N or Z. Okay, therefore, a discrete time random process is just a sequence of random variable. Okay, for this reason, discrete time random processes are sometimes referred to as or called a random sequence. We can denote such a discrete random process by this notation or this notation if index set is countable, or x of n equal to z, or x n equal to z. Okay, so when time is discrete, we can denote it by we have random sequence. Thus, we can when time is discrete, or random process is discrete time, or we have discrete time random process, we can write the stochastic process same as a sequence x1, x2, x3, and so on. Thus, we say that the process this is a discrete time random process. Discrete time processes are sometimes obtained from continuous time process by discretized time. Okay, for example, in temperature, we check or compute in any day at time at this time. Okay, for example, x1 equal to t of 110 okay, after 25 or 1 day, check or write temperature, and after 2 days at this time this. Okay, this is discrete. This is discretized time of continuous time random process. So x1, x2, x3, and so on is discrete time random process. Okay, by this means we can change a continuous time random process to a discrete time random process. And in general, xn equal to t of t index t. That by this manner, tn equal to this value, okay, for each t. xt is a discrete time random process. Figure 10.2 shows possible realization of this random process. See, this is temperature. Okay, we select at the same interval time observation. Okay, t1, t2, t. This is continuous time. This is discrete time. So we can change continuous time random process to discrete time random process. So the definition: a continuous time random process is a random process same as xt, t belong to G, where G is an interval same as this, or this. But for discrete random process that we call random sequence, sometimes we call random sequence, is this random process, okay, where G is a countable set. G is countable set. Okay, don't be tired. We can show any random process same as a random function. Random function is a function that take the value at random. So consider a random process xt, t belong to G. This random process is a result from a random experiment. Okay, you define a random for random experiment. Come back in the first or chapter 2 and study the random experiment. Random experiment construct a random variable by my bits, but at each time we find the value of x of t. By this means we can collection of the observation or collection of a random variable. For example, observe the stock price of a company over a period of time. Remember that any random experiment is defined on a sample space S. Come back in a previous chapter and learn sample space, the definition of sample space. After observe the value of xt, we obtain a function of time, such as one shown in figure 10.1. The function shown in this figure is just one of the many possible outcomes, okay? Because at each time you may take any value. For example, see. For example, for this realization, at time t, you just obtain this value, but may in a day below this, the value that you find below this or upper this. Okay, so at each time you have many time that you see only one time. Okay, for example, in 1 year and t2 days you keep this value, but for another year and this day may this value change greater or equal or itself. Okay, the function shows in this figure is just one of the many possible outcomes of this random experiment. So may you take another value for this day, but in other year. Okay, we call each of these possible function of xt a sample function or sample path. It is called realization, the value that we see of x at t. From this point of view, a random possible can be thought of as a random function of time. You are familiar with concept of function. The difference here is that t belong to G will be equal to one of many possible sample functions after we are done with our random experiment. In engineering application, random processes are often referred or called as random signal. So, with definition, a random process is a random function of time. Let's see this example. Example 10.1. We have $1,000 to put in an account with interest rate R. Okay, you your capital give to the bank and with this rate increase. Okay, compute computed annually computed annually. Okay, if we uh, take give to bank $1,000 after 1 year, how many give to me? Okay, that is, if xn is the value of account at year end, then xn equal 1000 multiple this value of power n take 0. If n take 0, the initial value. If n take 1, after 1 year. If n take 2, after 2 years, this is increased the money. The value of R is random variable that is determined when you put the money in the bank, but does not change after that. Okay, every person with one rate give the money in the account to the bank. Okay, at the first bank selected R, but after this time R not change. The value of R is a random variable for the time that you put the money in the bank, but it is not change after. In particular, R, suppose R be uniform distribution over this interval. For uniform distribution, go back to the previous chapter and find uniform distribution and study the properties. A. Find all possible sample function for random process. Okay. B. Find the expected value your account at year 3. That is, find expected value of x index 3 solution. Here the randomness in x comes from the random variable R. As soon as you know R, okay, is a uniform distribution, so at the first you selected uh, selected random a number at this interval, say r. Okay, so by this formula you can calculate, okay, if r is known, you can calculate your money at end of each year. Take n0 is 1000, the initial money. Take 1, okay, calculate, this give to you the money after 1 year, and so on. Okay, this is all realization or all sample pass. If for each r you have a sample pass. The random variable x3 is given by this, so we can calculate the expected value. For simplicity, define y equal to 1 plus r. Y is uniform distribution between this. Okay, come back, in previous chapter and study uniform distribution and their properties. So f of y, this is not this, okay? This is only 1 plus r. This is density function. This is density function. You must, density function for uniform is 1 upper difference the end interval minus first point of interval. Okay, this. So for calculate the expected value, calculate this. This is constant, come back out from expected. So we must calculate the expected y3. This is constant. This calculation y multiplied by this, okay, y3 multiplied by this density function, take integral over this interval, okay. By lotus means how we can come back to the previous chapter, how we can study how we can calculate expected value of a function of random variable. Take this integral and replace the value, and simplicity after 3 years the expected value of your money reach to this value. Another example, let xt t belong to this interval defined by this notation. This is a random process. Suppose A and B are independent normal distribution with mean 1 and variance 1. Come back in the previous chapters and study the normal distribution. Okay, see the function of density function for normal density function. Find all possible sample function for this random forest possible. Define the random variable y equal to x1. Find the probability density function of y. Come back to the previous chapter and study probability density function. And C, let z equal to x2. Find expected value of y multiplied by z. For the solution, for the solution. Here we note that the randomness in xt comes from two random variable a and b. Okay, the random variable a can take any value same as a belong to R, and b also take any value in the R. Okay, for example, if a equal to a, okay, means you select random variable between minus infinity up to plus infinity, call a. Similarly for b, then xt equal to a plus bt. This is sample pass. Okay, for each value of a and each value of b, you have a sample pass. This is general sample pass. Okay, so we have y equal to x1 means a plus b. T is 1. Okay, take t1. A and B are independent, normal, so the expected value of y is expected value A of B. The expected value come back in the previous chapter and study the properties of expected value. The expected value of sum equal to sum of expected value. A is normal, the mean is 1, variance is 1, so the expected value is 1. Similarly for B, so this is 2. For the value of variance, the variance is sum of variance if A and B are independent. So come back in the previous chapter and study the properties, the definition of variance and properties. This detail you must know. Okay, in the course of that previously in BS degree in university you pass. So the variance of sum, since A and B are independent, is variance A plus variance B. Variance A is 1, variance B is 1, so this is right. Thus, we conclude that y, when x normal, y normal, the plus of two independent normal is also normal. So we must only calculate expected and variance. So the above calculate this. The result y is normal with mean 2 and variance 2. The density function of x1 is this. This is normal with mean 2 and variance 2. Come back in the previous chapter and study normal distribution. This is part B, and for part C, expected value y multiplied by z, replace this, okay? Replace y and replace z, multiple expected value sum equal to sum of expected value. This is A and B are independent. If x and b are independent, if two random variables are independent, the expected value of multiple equal to multiple expected. Okay, yes. Since A and B are independent. This is 2, this is 2, this is 1, this is 1. Calculate, you paid 9. The random process in the above example were relatively simple in the sense the randomness in the process original from one or two random variables. We will see more complicated example later on. Okay, don't be tired. Lesson and begin section 10.1.1. The name of this section is probability, density function, and cumulative distribution function. For the meaning of probability, density function, and cumulative distribution function in general for a random variable, go into the chapter 4 and study these topics. Consider a random process same as this, where for any t0 belong to G, x of t0 is a random variable. So we can define cumulative distribution function, and if continuous, if xt not continuous in time, continuous for the value of x. We can define the probability density function. If x is discrete, we can define the probability mass function. So in general, if x is continuous, not in time, continuous for value of x at time t, or discrete, we can define cumulative distribution function same as this, okay? Denoted cumulative distribution function with f big, okay, index x of t0 at point x0. This means a probability for this event x t0 less than or equal to x. If for two times t1 and t2, we can define the joint cumulative distribution function of x of t1 and x of t2 by this notation. And generally, for n point of in time, we can define this. Okay. So if x is continuous, we can derivative with respect to x and obtain probability density function. So you read in the previous chapter probability density function, cumulative distribution function, probability mass function, joint probability density function, or joint cumulative distribution function. Come back in previous chapter of this book and study these details. Consider an example. Consider the random process xn. N can take 0, 1, 2, and so on, n index set, in which xi are iid standard normal random variable. Iid means independent identical distributed, means x for each n have same distribution, and distribution are standard normal. Come back and study normal random variable. Now write down f of xn at x. This is probability density function of xn for each time 0, 1, 2, and so on, and write joint probability density function for xm and xn. For solution, the first type, since xn is a normal distribution with standard, that is mean is 0 and variance is 1, the formula for probability density function of x is same as this. For xn is normal standard. So this is probability density function at time for random variable xn for each n. The part 2, if m not equal to n, xm and xn are independent, because in the problem this xn are iid, same distribution and independent each other. So xm and xn are independent. For we find joint probability density function if xm and xn are independent, the probability density function equal to multiple of marginal density function. For each replace the formula multiple, you can get this joint density function for xm and xn. Take break. Subsection 10.1.2. 2. The name of the details of subject in this subsection is mean and correlation function. Since at each time x of t is a random variable, we can study the properties of random variable. The famous property of a random variable is means or expected value, variance, and correlation function. For these details, you can go back in chapter 3 and chapter 4 and study mean or expected value and variance of a random variable. So, for the definition of mean of a random variable, see these sentences. For a random variable xt, the mean function denoted by mu index x of t, that is a function from a state space, from the space of time t to a real value, and defined by this. Okay, defined by this. The meaning of this must be multiple x of the density function and take integral if x is continuous and x is discrete, not time, x. And if x is discrete, the expected value equal to sum x multiplied by probability mass function. For the definition of expected, go back in chapter 3 and chapter 2 and study details. If time is discrete, we denoted the expected value by this notation. Some book denoted a mean function by mx of t or this, but we choose in this book denoted by this notation for discrete time random variable and this notation for continuous time random variable. For example, if xt is a temperature, because the expected value is a function of time, if xt is temperature in a certain city, the mean function mu might look like the function shown in figure 10.3. Okay, for this, this is mean function, but the value occasionally go up and down around this. This is mean function. So let's see this example. Find the mean function of random process given in example 10.1 and 10.2. So in 10.1, xn for n 0, 1, 2. By definition, this is by definition when time is discrete, okay, is the expected value of this a constant comeback out from expected. Yn we have y in the example 10.1 y equal to 1 plus r, that is uniform over this interval. So we multiply y power n multiplied by density function. Take integral this, okay, this. So the upper bound and lower bound integral, one time replace this minus, one time replace this, okay, and calculate this simplicity, or this is function of n, okay, this is function of t, okay, t is in this example denoted by n. This is mean function. For the example 10.2, t belong to this interval, time is continuous, the expected value, replace xt. The expected value is for sum of random variable equal to sum of expected value. Go back in chapter 3 and chapter 4 and study the properties and definition of expected value. So t is constant, come back out. A is a random variable. The expected value is 1 because A is normal, B is normal, which means 0, which means this is example of 10.2. Okay. This is example 10.2. This is A is normal with expected value 1, B is normal with expected value of 1, okay, 1, 1. Okay, so replace 1 and simplicity, this is a function of t, okay, this is mean function. Take break and come back to continue. Covariance. The mean function mu give us the expected value of x at time t, okay, but it does not give us any information about how xt1 and xt2 are related. To get some insight on the relation between xt1 and xt2, we define the correlation and correlation function. Let xt be a random process, autocorrelation function, or simply correlation function denoted by R x T1 T2. That means calculate the relation x at time t1 and x at time t2 is defined by this expected value. Okay, expected value of multiple xt1 cross xt2. This is correlation function. Okay, this is named autocorrelation function, or this is named autocorrelation function or correlation function for simply. Another case, for random process xt, the correlation function or simplify autocovariance function or simply autocovariance function denoted by C index x at point t1, t2 and defined by this notation. Okay, and defined by this notation. Note that if t1 equal to t2 equal to t, okay, if the value of t1 same as value of t2, the autocorrelation function by definition above is this same as this, so x power 2 expected value of this, and autocovariance function equal to variance. Okay, by definition, if xt1 not equal to if t1 not equal to t2, the autocorrelation function can define by this, and you can multiply, and if this multiplied by this and expected sum equal to sum, we reach to, and simplicity, you reach to this formula. And let us solution an example. Find the autocorrelation function, find the correlation function and covariance function for random process given in example 10.1 and 10.2. For the problem 10.1, for correlation function, we calculate R, same as this, is this value. Okay, this is y is 1 equal to 1 plus R is uniform distribution by definition of expected value. Okay, this multiplied by this value, calculate the integral, obtain this correlation function. For covariance function, this value is this minus this value. Okay, firstly calculate this, replace, multiple, and simplicity, you reach this notation. For other example, okay, this autocorrelation function by definition is this, replace the definition of x, multiple, and expected value is equal to Value of sum of expected value, replace the value, reach this value. Finally, for autocorrelation is this minus this by definition, replace the value and simplicity, reach this formula. This is covariance function. For example, 10.2. Okay, take break and come back to this subsection 10.1.3 with name multiple random process. We often need to study more than one random process. For example, when investigate in the stock market, you consider several different stocks and you are interested in how they are related. In particular, you might be interested in finding out whether two stocks are positively or negatively correlated. A useful idea in this situation is to look at cross correlation. This is a topics, okay, and cross covariance function. So let's define the cross correlation function and define cross correlation function in this figure. For two random processes xt and yt, the cross correlation function denoted by r index x and y at time t1 and t2 is defined by r index xy t1 t2 equal to expected value multiple to random process at t1 and t2. For each t1 and t2 belong to index set G. This is definition of cross correlation function. Cross correlation function. What definition of cross covariance function denoted by this notation? C index xy at 2 points and define covariance x t1 and y t2 defined by cross correlation function minus multiple of two expected value of random processor x and random processor y. To get an idea about this concept, suppose xt is the price of oil per gallon and yt is the price of gasoline per gallon at time t. Since gasoil is produced from oil, as oil price increase, the gasoil price tend to increasing too. Thus, we conclude that xt and yt should be positively correlated, at least for the same time, okay, at least. That is the value of covariance function must be positive. See example. Let A, B, and C be independent normal with mean 1 and variance 1. Okay, so you have three random variables. A is a random variable, B is a random variable, C is a random variable. These three random variables are independent. For the meaning of independent, go back in the previous chapter 3 or 4, and study the subject of independent. And distribution are normal with mean 1 and variance 1. And let xt for t belong to this interval defined by this notation. Okay, xt is a random process, is a plus b multiplied by t, and yt be another random process and divided by this. A is the same, but b changed to c. Okay, so must find uh, we must find correlation function and covariance function for T1 and T2. Solution: mu of xt is previously we calculate in the at first this lesson. Expected value of xt, replace xt, and expected value sum is equal to sum of expected value. T is constant, come back out. The expected value A is 1. The expected value of B is 1 because this is normal with mean 1. Similarly, this calculate for y. This is mean x, this is mean y. So for calculate correlation correlation function, must be defined expected value of xt1 multiple yt2, replace x and replace y, multiple this parenthesis multiple by this. Okay, you get to 4 10. Expected value of sum equal to sum of expected value this, expected value this. T2 is constant, come out from the expected value. T1 is constant, come out of this expected value, and similar. So this is expected value A2. A and C are independent. The expected value of multiple equal to multiple of expected value. B and A is independent. Expected value multiple equal to multiple expected value. And similarly for C, for B and C. So this is expected value of A2 is by definition variance equal to 1. Go back and use the definition of variance equal to expected value power 2 minus expected power 2 of a random variable. Replace, you reach this value. Expected value A is 1, expected value is 1, this is A2. Replace the value and simplicity reach to this figure. Okay, use use the use this calculation and calculate covariance function. Covariance function is correlation function minus multiple of expected value. Correlation calculate above, replace this value minus expected value of x is this value and expected value is this value. Calculate above and simplicity, multiple simplicity reach to 1. Take break and come to this subsection 10.1.3 with name multiple random process. We often need to study more than one random process. For example, when investigate in the stock market, you consider several different stocks and you are interested in how they are related. In particular, you might be interested in finding out whether two stocks are positively or negatively correlated. A useful idea in this situation is to look at cross correlation. This is a topics, okay, and cross covariance function. So let's define the cross correlation function and define cross correlation function in this figure. For two random processes xt and yt, the cross correlation function denoted by r index x and y at time t1 and t2 is defined by r index xy t1 t2 equal to expected value multiple to random process at t1 and t2. For each t1 and t2 belong to index set G. This is definition of cross correlation function. Cross correlation function. What definition of cross covariance function denoted by this notation? C index xy at 2 point and define covariance x t1 and y t2 defined by cross correlation function minus multiple of two expected value of random processor x and random processor y. To get an idea about this concept, suppose xt is the price of oil per gallon and yt is the price of gasoline per gallon at time t. Since gasoil is produced from oil, as oil price increase, the gasoil price tend to increasing too. Thus, we conclude that xt and yt should be positively correlated, at least for the same time, okay, at least. That is the value of covariance function must be positive. See example. Let A, B, and C be independent, normal with mean 1 and variance 1. Okay, so you have three random variables. A is a random variable, B is a random variable, C is a random variable. These three random variables are independent. For the meaning of independent, go back in the previous chapter 3 or 4, and study the subject of independent. And distribution are normal with mean 1 and variance 1. And let xt for t belong to this interval defined by this notation. Okay, xt is a random process, is a plus b multiplied by t, and yt be another random process and divided by this. A is the same, but b changed to c. Okay, so must find uh, we must find correlation function and covariance function for T1 and T2. Solution: mu of xt is previously we calculate in the at first this lesson, expected value of xt, replace xt, and expected value sum is equal to sum of expected value. T is constant, come back out. The expected value A is 1. The expected value of B is 1 because this is normal with mean 1. Similarly, this calculate for Y. This is mean X, this is mean Y. So for calculate correlation correlation function, must be defined expected value of xt1 multiple yt2, replace x and replace y, multiple this parenthesis multiple by this. Okay, you get to 4 10. Expected value of sum equal to sum of expected value this, expected value this. T2 is constant, come out from the expected value. T1 is constant, come out of this expected value, and similar. So this is expected value A2. A and C are independent. The expected value of multiple equal to multiple of expected value. B and A is independent. Expected value multiple equal to multiple expected value. And similarly for C, for B and C. So this is expected value of A2 is by definition variance equal to 1. Go back and use the definition of variance equal to expected value power 2 minus expected power 2 of a random variable. Replace, you reach this value. Expected value A is 1, expected value is 1. This is A2. Replace the value and simplicity reach to this figure. Okay, use use the use this calculation and calculate covariance function. Covariance function is correlation function minus multiple of expected value. Correlation calculate above, replace this value minus expected value of x is this value and expected value is this value. Calculate above and simplicity, multiple simplicity reach to 1. Take break and come. Subsection 10.1.4 with name stationary process. What's the meaning of a stationary process, or what is concept of a stationary process? See this paragraph. We can classify random process based on many different criteria, different condition. Okay. One of the important questions that we can ask about a random process is whether it is a stationary process intuitively. Okay, a random process xt is stationary if its statistical properties do not change by time. Okay, means the expected value is constant, not depend on time. Variance is constant and doesn't depend on time. Covariance function depend on difference between time. The distribution function is not changed by time. Okay, if you have a stationary process, you must these properties. Intuitively, a random process xt is stationary if its statistical properties does not change by time. For example, for a stationary process, xt and xt plus delta, delta is any time, okay? Time change, okay? Have the same probability distribution. In particular, f of xt at point x equal to f of xt plus delta. Delta is another time at x. More generally, for a stationary process, the joint distribution xt and xt1 and xt2 is the same as the distribution of xt1 plus delta, and joint distribution, multiple distribution of this equal to multiple or joint distribution of two random variable at this point and this point. For example, if you have a stationary process of xt, the probability of xt1 and xt2 belong to A. A is a subset or a set in R2 equal to probability of xt1 plus delta and xt2 plus delta belong to A. In sum, a random process is stationary if a time shift does not change its statistical probability. Here is a formal definition of a stationary continuous time process. In this rectangle, a continuous time random process xt is strictly sense stationary, or simply we say stationary. So if we say stationary means strict sense stationary. If for all T1, T2, Tr and all delta, the joint CDF of this is the same as the joint CDF of this. Okay, means the cumulative distribution function CDF of multiple random variable equal to CDF of this. We can provide similar definition for discrete random process. Okay, for strictly sense stationary or simply stationary for discrete time random process, if for all n1, n2, and r belong to z, z is integer number and d is subset of integer number, the joint CDF, this sum random variable equal to CDF of this, means change time at with same time b does not change the distribution function. Okay, so this two distribution must be equal. So if you impossible does not understand some detail that we said for you, this may be that you have knowledge about any term of probability. So I say to you, go and study Introduction, Chapter 1, Chapter 2, Chapter 3, up to Chapter 10 in this book that I upload above this course. Thank you. Subsection 10.5 with name Gaussian random process. For that you better understand the subject of this subsection, come back in previous chapter and study the normal distribution. Okay, normal distribution and the Gaussian random variable are same, but a Gaussian random process is a collection of random variable that each random variable have a normal distribution. So you must learn and understand the concept of and properties of a normal random variable in previous chapter. This random variable is continuous value and continuous time process. Is a famous of a random process that we need of this very important. Here we will briefly introduce normal or Gaussian random process. We will discuss some example of Gaussian process in more details later on. Okay, so it's important. Many important practical random process are subclass of normal random process. First, let us remember a few facts about Gaussian random vector. As we saw before means previous chapter, not in chapter 10, chapter 3, chapter 4, and so on. Random variable x1, x2, xn are said to be jointly normal if for all a1, a2, an belong to R is real number, the random variable this for, okay, each random variable multiplied by each a and sum to each other is a normal random variable. So we learn the sum any linear combination of Gaussian or normal random variable is also a normal. Also, a random vector x1, x2, xn is a column vector, okay, denoted by x is bold, is said to be normal or Gaussian if the random variable x1, x2, xn are jointly normal. An important property of jointly normal random variable is that their joint PDF is completely determine their mean and covariance matrix. More specified, for a normal random vector x with mean m and covariance matrix C, the PDF probability density function is given by this notation. Okay, this is determinant. Now, uh, if any subject, if any subject for previous time that you get graduate degree of BS or MS in university, search in Google, okay? Search in Google, same as type determinant, okay? Determinant matrix. Give to you a definition. Now, let us define Gaussian random process. A random process xt is said to be a Gaussian random process if for all t1, t2, and tn belong to G, the random variable x1, x2, xn are jointly normal distribution, means the distribution function is same as this. Example, let xt be a zero mean y sense y sense stationary. White sense stationary means white sense station or weak sense stationary means expected value independent of t. Variance is independent of t, and the covariance or correlation depends only on difference time t1 and t2. That in this type t2 minus t1 denoted by tau. Okay, so wide sense stationary or weak sense stationary Gaussian process with this correlation function for all tau, find the probability x1 less than 1. Find the probability x1 plus xt less than 1. Xt is a normal random variable with mean xt1 equal to 0. Okay, because this xt be a zero mean. Since xt is 0 mean, the expected value is 0. And covariance and variance, okay, variance, this definition, because xt is 0 mean, the variance is expected value of x1 power 2. Xt be a zero mean wide sense stationary Gaussian process with this correlation function. Give me this correlation function means if a stationary wide sense wide sense stationary, the correlation function is this manner. Find the probability of xt1 less than 1 and the probability of some two value at t1 and t2, okay, 1, 2, less than 1. Xt is a normal random variable with mean uh, 0, because in these sentences say to me that 0 mean, xt is 0 mean, and covariance and the variance is this. For the variance of xt, okay, equal to expected value of x2 minus expected value power 2 xt. Okay, this is 0, this is 0. Okay, so the variance equal to expected value of x power 2. X power 2 from the this is r by definition r be expected multivariate xt1 and xt2. The difference between t1 and t2 is tau, so rx at 0 point is 1. Thus the probability of x1 less than 1 is a distribution function, a standard from 1 difference mean and divided by a standard deviation, a square root of variance. Okay, take phi at 1, table of normal, okay, table of normal distribution. If this is figure normal, at this point is 1. This area is 8.4 font. Okay, similarly take y equal to x1 plus x2, then y is a normal random variable, because the above we say that each, if x1 and x2 is normal, each linear combination of these are normal distribution. The mean of y is mean of this, mean 0, 0, 0. Variance of this is variance xt T1 variance xt2 plus 2 covariance. Come back in previous chapter and study this notation. Not that variance x1, okay, same as this manner, is variance minus this. This is r x0, this is this is 1, this is 0, 1, and equal to variance x2. So you can replace in covariance by the above calculation. Correlation function. Correlation function by definition is this. This is Rx at minus 1, 1, minus 2, minus 1, minus this is expected value. Expected value are the same. Each is 0, sum this or 0. This is e power minus 1. This covariance is this. So variance of y equal to 2 plus 2 over e. So y is normal, which means 0, and variance this value we can compute. We can compute y less than 1 is phi. Subtract mean of y from 1 and divided by square root of variance. Okay, this is this value, and come back in table normal, and come back in table normal, specify this value, okay, specify this value. This area is this value. An important properties of normal random process is the wide sense stationary and strict sense stationary are equivalent for this process. Okay, means if the random vector are Gaussian process, the wide sense stationary and strictly stationary are equivalent. But if x are not Gaussian, strictly stationary imply wide sense stationary, but the converse is in general is not true. More generally, we can state the following theorem. Consider the Gaussian random variable xt. If xt is wide sense stationary, then xt is a stationary process. We need to show that t1, t2, tr belong to r, and delta is another value specified in r. The joint CDF of this collection is same as the joint CDF of this collection. Since these random variables are jointly Gaussian, it suffices to show that the mean vector and the covariance matrix are the same. Okay. To see this, note that xt is a wide sense stationary process, so mu of each x at each time are equal and does not depend on t. The covariance matrix x at t I plus delta and Tj plus delta, same as covariance matrix as at Ti and Tj, because is white noise depend only different type, not initial or end point type. Equal this denoted or show by this notation. From the above, we conclude that the mean vector and the covariance matrix of this are same as this. Okay, so this means that the when the vector is Gaussian random process, the mean and covariance or correlation function, if we shifted type, is not changed. Similarly, we can define jointly Gaussian random variable. Two random variables x and y are said to be jointly Gaussian normal if for each t1 up to tn and t1 prime up to tn prime, the random vector, all two sets of collection are jointly normal. Okay. Note that from the property of jointly normal random variable, we can conclude that if two joint Gaussian random processes xt and yt are uncorrelated, means covariance function is 0. Then xt and yt are independent random variables. This is true only for Gaussian random process. Okay, if two random processes are independent, covariance matrix or covariance is 0. But the converse is not true, only if the jointly are normal random process. Thank you.